Thank you very much. First of all, thanks for giving me the chance to speak, and thanks for organizing this wonderful conference. It's been a great time here. Okay, let me dive right into it. So, my name is Pascal Fries. I'm an IT consultant at Artix in Munich. What I focus most on is Kubernetes, monitoring Kubernetes, but also setting up Kubernetes, doing CI/CD in Kubernetes. And as the infrastructure below that, I love to do infrastructure as code. So if you have any Terraform questions, feel free to ask me those. But generally, what I do could be summarized as cloud stuff or cloud native stuff. Okay, great. There are still some people left. Who of you is using Kubernetes? Raise your hand. What are the other ones using? Oh. Yeah. I'll count that as Kubernetes. Okay, so of those who use Kubernetes, who's using a single cluster? So I guess most are using a multi-cluster, right? Raise your hand if you're using multi-cluster Kubernetes. Yeah, that's my impression. So Kubernetes was built in mind with role-based success and the possibility to separate applications within a single cluster. So actually, it should be easy to deploy your applications in a single cluster and to maintain a single cluster only. That's why many components that are targeted or many applications that are targeted to be infrastructure for Kubernetes actually also only target a single Kubernetes cluster. Now, who's using Prometheus with Kubernetes? And of those who are using Prometheus, are you just using Prometheus or are you using anything on top of that? Raise your hand if you are using it standalone without anything else. Yeah, that includes, yeah. No, I mean like anything built on top, like just Prometheus or Prometheus with, say, Thanos, or Prometheus with anything else that grants you persistence, the possibility to monitor multiple clusters. Okay, then standalone. That's great. So the thing is, actually, Kubernetes and Prometheus work very well together, right? That's the reason why we use it in Kubernetes. There is automatic service discovery. There is the Prometheus operator, which simplifies deployment of Prometheus in Kubernetes, which simplifies setting up the service discovery, deploying service monitors, pod monitors. And all of that can be deployed with a single Helm install by the Prometheus stack Helm chart. Now, if you do multi-cluster, and most of you said that you are doing multi-cluster, it's still easy. Sure, we can do multi-cluster. Just use one Prometheus or one Prometheus operator per cluster, and you're happy. Now, this is where the story ends if you're using just Prometheus. Now, let's say you're in the situation where you have multiple clusters, you have multiple Prometheus or Promethei or whatever you want to call it, and you want a common endpoint. So you want one place where you can get all of your metrics. Still, you can use Prometheus. You have several ways of setting that up. You can use the remote write protocol, you can use the remote read protocol, and you could also use just federate endpoints. However, as you might set this up, you might encounter some problems, and these problems are with why you would usually want to set up this in the first place, right? You want to set up, in the end, you want to send up a single place where you can get all of your metrics, but usually not everyone is cluster admin. Not everyone should be entitled to get all your metrics. And if you want to set up a place where you can get all the metrics, where do you store that? Like, how do you get so much space on your disk? So, first of all, that seems pretty awesome, but you run into the problem that you have no way to deal with long-term storage. The default retention time or the recommended retention time on a single Prometheus instance should be 1 or 2 weeks, not too much more, because then you'll run out of space. How would you build up redundancy? So if one of your Prometheus drops out, say you have this single point where you can grab all of your metrics. If this single point fails, where do you get your metrics from? So you don't have any way of high availability. And the last thing is, how do you deal with multi-tenancy? So in the usual sense, you're not alone in your cluster. There are several people there. There are several people working on different projects across different clusters, and you want to assign who can read and who can send which metrics to this common endpoint. And that brings me to, there's something seems to be a little bit broken. And that brings me to a point where I'll tell you the story of a customer that I was working with. So at Artix, we help people also set up Kubernetes landscapes, meaning not just a single cluster, but several clusters, and how to manage them in the long term. And that includes monitoring. And this customer had the situation that they have one infrastructure team. This one infrastructure team is responsible for setting up the clusters, for maintaining these clusters, for setting up any infrastructure that's related to those clusters, and that includes Prometheus, or that includes anything that's related to monitoring. Then we have several teams that are working inside these clusters, so they should not be concerned with administrating them, or at least in the general case, they should not be concerned with administrating them. They just do development, deploy their test versions, or they are the operations teams that deploy the productive versions to those clusters and maintain those. Now, in this situation, we have like 20 plus clusters. So the scale of each of those clusters is around 1 terabyte of memory. That's Java applications for you. There's shared clusters. So there's like this cluster on the top left here, where you have the infrastructure team doing some stuff, where you have the developers doing some stuff, where you have a operations team doing some stuff. There's managed clusters for a single team, like this here. So you have a cluster that is managed by infra for the development B. And then there are also owned clusters, where, say, the operations team A is administrator of all of the cluster. Now, how to set up monitoring for this with mostly Prometheus might be a little bit tricky, because they had a very strict requirement, and the very strict requirement was infra should manage a single endpoint where everyone can get their metrics, so that everyone can run their own Grafana or whatever they want to do in order to grab all those Prometheus metrics. And this single point should provide everything, but depending on who you are, you get different metrics. They also have other requirements. The other requirements are they want long-term storage for the metrics, so they don't want to be limited to 1 or 2 weeks. They want high availability, so if that single point where you can get your metrics breaks down, they can just, it should not break down totally, so it should be replicated in some sense. And also, all of this should be push-based. And the push-based goes back to actually 2 things. One of the reasons why we have push-based is there are some owned clusters. So infra cannot set up anything in the owned clusters. They are created for a team, and then they're given to the team with the words "don't break it" or "it's gone." So this is something that infra will not be responsible for, but they still want to provide a way to send metrics there. So this is the reason why they chose push-based metrics delivery. Also, another reason is, of course, the reason that you have most times for using push-based metrics, networking. Like, some of these clusters cannot be reached from outside, you have to push from there. And then the setup doesn't work anymore. Right? Push-based still works because you can use remote write. High availability doesn't work anymore. It also doesn't work anymore if you want any kind of redundancy, so that if your hard drives fail, you have the chance of recovering anything. And also, long-term storage is not implemented in this picture. Entering the picture is Thanos. So there are several solutions to that, I should say first. So one solution would be Cortex. There's, of course, Mimir that we heard about today. Another solution that I'm really fond of is Thanos. And you can think of Thanos as a storage layer for Prometheus. So still you have the plain old Prometheus. It's doing what it does best, scraping metrics, storing them for a short amount of time. But then you put an extra component there, which is Thanos, which acts maybe as a sidecar. So the sidecar will allow you to grab Prometheus metrics from Thanos instead of Prometheus. So you can have a different API, basically. There's a query which can communicate with multiple sidecars. So basically, you could rebuild this picture over here just by using Thanos components, and we will see that in a minute. The cool thing is now you have an extra component that is in no way related to Prometheus, apart from providing the same API or being able to talk to Prometheus. Now, this extra component, the sidecar, could store your metrics in a S3 bucket. Like we're in the cloud now, so we use S3 for everything. And as soon as it's in the S3 bucket, basically your retention time is infinite. Especially if you have any chance of getting it out of the S3 bucket again. And that's what a store is for. And there's another component called receiver, which I will get to later. Okay, so why is Thanos cool? Why do I like it? So the thing about Thanos, it's truly cloud native, right? It embraces all concepts of cloud. It embraces the concept of statelessness. It embraces the concept of API-driven communication. It's a microservice application, and also which is the reason that I love it most. It's great for tinkering. Like there's several components to a Thanos cluster, and we will see what these are. And you can mix and match between them. You have loads of stuff that you can adjust. And if you're new to Thanos, you might break stuff, but it's remarkably resilient to misconfiguration. So to give you an example, the cluster that we set up at the customer, from the moment on that it worked the first time, and it's a microservice application, so we deployed individual parts of it, wired them up to work in some way. From that point on, we didn't lose a single block of metrics. And that's it's 1 year, which doesn't sound like a lot, but it's 1 year of tinkering around on the system, which could basically have been running productive because it didn't lose anything. And also it has a dark mode. Because the query, so this is the Thanos query, and the Thanos query it looks very much like the Prometheus query interface because it is the Prometheus query interface. That's the cool thing. If you work with Thanos, you don't have to think in any different way. It's just plain old Prometheus. It's just sitting in front of Prometheus and doing magic. Okay, so let me show you some sample configurations. So I talked about the sidecar before, and that you could use the sidecar to replace this federation thing that you can do with Prometheus. So why would you want to do this? Well, the first reason is because you can tinker around with Thanos then, but also you can make federation a little bit more efficient. And the reason why it's more efficient is because instead of using the REST and basic auth, the REST API and authentication via basic auth that you usually use with Prometheus, you use the sidecar to translate all these API calls into gRPC calls, which can also be where you can also do authentication with TLS client auth. So yeah, same picture again. every Prometheus gets a sidecar container. The sidecar itself can talk to Prometheus via the REST API, but the cool thing is the sidecar container runs alongside Prometheus, so network is fast. You could even give the sidecar container direct access to the time series database blocks of Prometheus. And all of these configurations that we see now, all of the communication that we see now is actually gRPC, which can be batched. It's a little bit faster. So now we haven't changed much. Let's try to change a little bit more. So at this point, we haven't really implemented any of these goals that we had in the first place. But how about implementing long-term storage? Now, if you want to implement long-term storage, it's very easy. Take the same setup as before. Just take an S3 storage and tell every of these sidecar containers, or every of these sidecar Thanoses, to store the data that they read from Prometheus also inside the S3 bucket. And now, as Prometheus just drops metrics at some time, like 1 or 2 weeks, they're still in the bucket. So as the sidecar pushes metrics to the bucket, they are backed up in a sense. Now, you could, of course, have this redundant in whatever way you want, because that depends on your S3 storage. But the cool thing is that you can also retrieve these metrics again via another Thanos component, which is called the store. So the Thanos store itself is stateless. And you can run it on top of your S3 bucket, or you can run it as any component with connection to the S3 bucket. And add it as another target in the query. And that's the other cool thing that I like about Thanos. All components can be queried by a querier. So if you have a sidecar, you can query it by the querier. If you have a store, you can query it with the querier. If you have a querier, you can query it with another querier. So you could build layered approaches, whatever you want to. So in this sense, we have solved long-term storage. What we haven't solved is high availability. Well, we have solved high availability for old metrics. Because for old metrics, we have a stateless Thanos store, and this could be replicated. And then we have like high availability for old metrics. But the new metrics that you can only get from the sidecar, because they have to be queried before they are pushed to S3, they are still not highly available. And that's something that we can also fix by switching to a push-based approach. And the push-based approach replaces the sidecar completely. So instead of using the sidecar, now we say we introduce another component, which is called the Thanos receiver. And the cool thing about the Thanos receiver is that it can be talked to via remote write from Prometheus directly. So Prometheus will scrape a metric, and as soon as it has this metric, it will trigger a remote write to the Thanos receiver. And at that point, data is in the Thanos receiver. It's not yet in the S3 bucket, because the receiver will only push blocks to the S3 buckets when there is enough data for that. But at the point that Prometheus scrapes metrics, they are immediately sent to the receiver. And instead of querying now a sidecar container, we query from the querier the receiver. As soon as the receiver has enough data collected, it will compactify that data into a block. That block will be sent to the S3 bucket, and the Thanos store can extract it later on. In addition, you can run compaction routines, which are called Thanos compact, which regularly look up data in the S3 bucket to see if they could be compactified into smaller or larger blocks, so that the index gets smaller. And this scenario actually solves all of the issues that we had. And also, it's a great use case of microservices. I like microservices, unlike many other people. Okay. So this is the point where I talk about how you actually can implement cool stuff within Thanos. So this last picture is the picture that we are using at the customer side also. So Of course, if you're running in production, you will have to take care that things are authenticated, that all API requests are authenticated. If you're using any API requests between components of Thanos, you can use TLS client auth. Between Prometheus and Thanos, say remote write, or the approach taken by the sidecar, you can still use basic auth as before. The important bit comes now about how do we build redundancy. That's something that I didn't talk about before because I haven't told you what the receiver actually does, instead, apart from taking over metrics and pushing them to S3. So the receiver acts as a short-time database. So in the picture that you saw before, data was first pushed to the receiver. So it acts kind of as a cache. And the cool thing is the receiver actually, as a stateful application, you can shard it, you can replicate the data. This is done by labels of the time series. It's a basic hash map, basic hash ring sharding. The bad thing about this is, of course, now say you have 6 receivers, or say you have a multiple of 3 receivers. You send your data in, and you want data to be replicated 3 times. So let's say we have let's say we have 9 receivers. There's data coming in. Data is selected by its labels to target. So every time series sample will be sent to 3 of these receivers as identified by its labels. That means that data is duplicated inside the receivers, and as the receivers send this data later on to S3, of course you will end up with duplicates in your S3. You will also end up with duplicates in the receiver, but that's not too bad because it's just a short-term storage. But you're wasting space in S3. You're also wasting resources when trying to query. Good thing is you can do deduplication. It's built into Thanos. So the query itself can deduplicate data. So as you saw on the previous slide, the query directly talks to the receiver. So the query sees this duplicate data, but it can deduplicate it again by using some external labels that are attached to each of the receivers. Also, the compactor, and that's the main reason why you should always run the compactor if you're using the duplicate stuff in your S3. The compactor also can deduplicate in S3, and that saves up a lot of space. Also, in the long term, it will downsample all of your data. So if you have 1 sample per minute, old samples will additionally be provided in a 1 sample every 5 minutes. And even older data will also be provided as 1 sample every hour, so that you can later on query time ranges spanning several months without breaking your API. Okay, so how do you actually implement high availability? Well, the querier and also the store, they are stateless. They just do your queries and that's it. So you can replicate them however you want. The receiver is stateful, but you can also replicate it. You will just have to take care that you configure the hash ring correctly. And you also will have to take care that there's enough storage for them, because at times there might be metric spikes if people send too much. So the receivers should always have enough storage to act as the short-term cache it's meant to be. And the compactor, well, it doesn't need to be highly available, because the compactor always runs in a cron-like fashion. It runs like every hour to see if there's new samples that need to be deduplicated. So it doesn't need replication. And lastly, I would like to show you a minimal model for multi-tenancy. And that's also possible in the previous picture. The general idea is, well, you take the compactor, and you just configure the compactor. It's written to via remote write. So it shouldn't be the compactor. It should be the receiver, sorry. The receiver, on ingestion of remote written labels, remote written samples, it applies a relabeling configuration and sets a tenant label. And this tenant label could be taken from, say, which cluster, which namespace do we match with which tenant. Then you configure your query in such a way that it's hidden behind a prom label proxy. And this prom label proxy actually forces the tenant label on any query that comes to it. And that's it. That's all you have to do. So the picture is still this. Right? Data goes to the receiver, will be written to S3. The querier can read from both S3 and the receiver. And the compactor will make sure that data is deduplicated and available in coarse-grained versions so that you can read it in the long term. And this is like one example configuration of that. So the querier is hidden behind a prom label proxy. The prom label proxy is hidden behind some authorization proxy. And the receiver has some basic relabeling rules, such as take the cluster and namespace label. And if they have this specific form, so if it's in the dev cluster and is app X or app Y, it will put the tenant label to dev B, and this prom label proxy actually forces the tenant label. What I can recommend is automated generation of this relabeling config, because it can be a pain. What I can also recommend is you can use the relabeling configuration to actually force some specific labels on untrusted data. So if anyone sends you whatever data, you can just drop it if it doesn't include this cluster and namespace label, so that in any case you will set a tenant label. And the bad thing about relabeling is currently relabeling configuration is only reread on receiver restart, and if you're running a big cluster, a restart of the receiver can take half an hour, because it can be a cluster of like 12 to 30 instances. They have to be restarted in order to not lose high availability. But there's an open issue for it, and people already commented that they are taking care of it. So it shouldn't take too long until it's fixed. Okay, so to conclude, we have long-term storage with Thanos. We have redundancy with Thanos. We can build high availability with Thanos. And multi-tenancy kind of works. Kind of works means if you never change your relabel config, fine, it works like a charm. Otherwise, not so much. There's also extra stuff that I didn't mention. There's also a Thanos ruler, which does the same thing for Prometheus rules, so alerting rules, recording rules. And there's also, if you have a really, really big Thanos cluster, the Thanos query frontend, which can actually shard Thanos queries to several different queries, which then target different receivers. And in that sense, you can get access to really big amounts of data. It's also taken from the Cortex project. Thank you very much. I think we have 1 minute left for questions. So I hope there is one.
So, thank you.